and I work in the power management work group in Linaro. This is the third time I have been presenting this presentation. We have already covered it twice. We are still doing it because we still have audience for this presentation. Let's see how many turn up today. So we are not going to very dive into the scheduler thing or go through the code or something. It is just an overview. The main reason why I started doing this is because when I started reading the scheduler code, I couldn't find much documentation, and getting through the basics was difficult. So once you understand how the schedule is laid out, you understand how a process gets scheduled, then everything is quite easy to follow. Of course, it is a complex beast, but still, you know how to read code at least. So the whole point of this presentation is to make sure people can start reading the code of scheduler, which is normally like a black box for most of the people. It is still complex, it is still quite complex, and to understand even like 20% of it is going to take a hell out of you, but you'll start reading at least. So this is the agenda for today. We'll see what the scheduler is, why do we need it, what was the previous scheduler which was used prior to 2007 when the new scheme came into place, and then we will see how the new scheduler is placed, what are the different scheduling classes, how a task runs, and which scheduling class gets a chance to run first, how a priority of a task decides how long it runs, and all that kind of stuff. So the scheduler. So to be clear, we are talking about the task scheduler here and nothing else. On a multi-threaded system, we have multiple threads which are running on a finite set of CPUs, and they all need a chance to run on the CPU to perform some activity. So the same CPU is shared between different tasks. The scheduler has to select a target CPU whenever a new task comes in, or a previous task which was running terminates, or it goes into sleep because it is waiting for a mutex or something, or some other event. If we are sharing the CPU between multiple tasks, each task have a time slice based on the priority. So once that time slice of 5 milliseconds or so completes, then we pick a new task. So at that time, the scheduler comes into place again, and it finds the next task to run on that CPU. So if you see, in one way, the scheduler code is not something we want to run on a CPU, because that is unnecessary churn of code which is there. What we really want to run is the task itself. There are 10 tasks in the system, and we want to run them. If the scheduler takes 50% of the time out of CPU, then we are screwed, because that is not what we want. It is a waste of time. So the scheduler should be as optimized as possible to make sure that the scheduler takes the least amount of time to do all this stuff, all this maintenance stuff. It is the task which should run all the time, or most of the time, I'll say. So there are various things which a scheduler has to keep into mind. One is, of course, the one which I just told, that it has to make sure that it runs for the least amount of time and give more time to task. The time given to task should be in a fair way. It should not be that a task is starved and all the other tasks are getting chances. A high priority task should always get a chance to run because of the priority it has. The time slice is, so in kernel right now, the time slice of a task is based on the priority of a task which a user sets. If a user sets a high priority for a task, that task should run longer compared to a low priority task. We should have low task response time. What we mean by this is whenever a task is made available to run by a programmer, the response time is the time the scheduler takes from that point of time to actually run the task for the very first time. That is the response time. So it should be really fast. The other metrics is the throughput. So throughput is how many tasks are completed every unit of time. So that should be high as well. We should complete as many tasks as possible as soon as we can. Now in SMP we have multiple CPUs and a lot of tasks. So the scheduler should take into account that we should not put all the tasks on a single CPU or two CPUs only, because the other CPUs will be unused. It may be good for power, but it will be bad for performance for sure, because there are CPUs available to run, and we should utilize them to run the tasks which are already waiting for it. By default in kernel, the scheduler is programmed for performance. So whenever a new task comes in, we try to pick an idle CPU, whichever is there, and run the task on it, even if it is not optimal for power savings. But that is the policy. We still go for performance first. And another important thing is that because the scheduler code is very central to the kernel, it is the same piece of code which runs on any architecture or computer system you are aware of, from mainframes to desktop to watches to laptops to everything, to phones. It is the same part of scheduler code which runs on every piece of it, and whenever we are trying to update it, we have to be very careful that it doesn't break x86, for example, or servers, for example, because that is just not allowed. So going back to the history, this is what you find in textbook. I don't know if the textbooks are updated to have the latest scheduler. So what we used to read earlier, 10 years earlier, was the O1 scheduler. The O1 comes from the complexity it has and the amount of time it takes to NQ or DQ a task. And that is O1 here. So whatever the number of tasks is, the scheduler will pick a next task in a very finite amount of time, and that is fixed. That doesn't change with the number of tasks. That is why it is O1. So in those days, we had 140 priorities. 0 to 99 priority was for the RT task, real-time task, and the other priorities from 100 to 139 for the user task. Now each CPU used to had each CPU's run queue. Run queue is a queue of tasks for the CPU to run. Now each CPU has its own run queue because it has to run the task by itself. So if there are 4 CPUs in the system, there will be 4 run queues, each local to the CPU. Each run queue used to have 2 arrays. One was the active array and one was the passive array. By active array, we mean that the next task to pick will be picked from the active array. And passive array is whenever a task finishes its time slice, or when we are done running it, it goes to the expired array. And once, okay, I'll come to that later. Now, these 2 arrays both had 140 entries, 1 entry for each priority. And each entry is actually a linked list of tasks. So I'll show that by this example. So if you see this, this is from a run queue of a single CPU. It has 2 arrays, one is active array, one is expired array. It has 140 entries. Each entry is a linked list for one priority level. So for priority 0, this is the linked list. For priority 1, this is the linked list. If we do a simple round robin, a CPU will always start from here, run all the tasks in this priority, then priority 1 up to 139. Once there is no other task left on this particular array, we switch both the arrays. This becomes the active array, this becomes the expired array, and the CPU starts executing tasks from this array. This was simple at that time. Because checking how many tasks are available in a particular array is difficult and time consuming all the time, we used to have a big bit mask of 140 bits, and so if the priority 1 linked list had any task, that particular bit in the bit mask was set to 1. So we can check with a single compare instruction if the active array of a CPU has any task or not. So it was linked list. We had a bitmap. There were time slices given to all the tasks based on the priority they were given by user space. So this is the story which was there until 2007. In 2007, this was replaced by CFS and few more scheduling classes. It is completely changed. We don't have O1 scheduler right now in kernel at all. the current design was introduced in 2623 by Ingo Molnar. It was, so the basic idea now is that we have scheduling classes. I'll go through the details of these. Scheduling class defines more or less the priorities in a broad way of tasks. So, and then these scheduling classes have different policies. For example, round robin or FIFO, right? So we have different policies within the scheduling classes to decide how the tasks within the scheduling class are going to be run, one by one or with a time slice, or how is it? The scheduling classes have their own priorities. So a higher scheduling class, a task from a higher scheduling class will always run before a task in a lower scheduling class. Tasks can migrate between CPUs and between scheduling classes. We can also move them between scheduling domains. There are syscalls for that. You can just call them and for a task, and the task will be moved between the scheduling classes and domains. These are the scheduling classes we have right now. The highest priority one is the stop scheduling class. The second one is deadline, then real time, then CFS, completely fair scheduler, and the last one is idle. Now, why this picture is shown this way is because this is the structure which is used to represent a scheduling class. The first entry is the next scheduling class. So this is the pointer. So this is present as a linked list. All the scheduling classes are present as this linked list in the kernel. And whenever we have to find a task to run next, we go through this linked list to see which scheduling class has a task available that we can run. The scheduling class has many other functions as well. For example, enqueue a task to the scheduling class, dequeue it, find the next task to run, and so on. There are many APIs for that. So this is the schedule function which you must have seen at many places in the code, which is called. This is the function which is responsible to pick the next task to run on the local CPU. Now what this function does is it picks a next runnable task for the CPU, searches for the task at the highest priority scheduling class, which is the stop scheduling class. We have a simple helper also, which it uses for each class, and this calls pick next task of each scheduling class one by one. So this is the main crux of the routine. So what it does is it runs through all the scheduling classes which are there based on the priority, based on the linked list we have seen here. So it starts from stop. For each class, it calls pick next task. If this routine returns retry task, it means that it is possible that a task has been added to a higher priority scheduling class and we should start again. So if the return is retry task, we start everything again from the stop scheduling class. Otherwise, either it will return a valid task or it will return null. If it returns null, then we go to the next scheduling class and try to pick a task from there. So what happens here is if for example, both deadline and CFS have some running task available, then when we run this loop, we will automatically pick a task from the deadline scheduling class first, and then only we will go to CFS and not before that. This is the list of all the scheduling classes we have in the kernel today. The highest priority one is stop scheduling class. It is a very special scheduling class. No user task goes to the scheduling class. It is used only for maintenance within the kernel to stop everything and run some kernel specific routines. Only these three in the middle are for running user programs. The last one, idle, is only used for CPU idle to put a CPU in a deep idle state. And so no other user task is also queued to this particular scheduling class. And so both of them don't have any policy. They're just scheduling classes with one thread for each CPU, nothing else. The highest priority scheduling class where a user task can go is the deadline scheduling class. It is also added recently, not long back. It has only one policy, sched deadline. The second priority goes to real-time task. It has two policies. FIFO and round robin. In FIFO, a task which is queued first gets a chance to run until it finishes or until it gives gives the CPU away. For example, when it sleeps or waits for an interrupt or something else. In round robin, we give a time slice of 5 milliseconds to 100 milliseconds. I think it is 100. 5 milliseconds is the default value. So after every 5 milliseconds, the next task from this round robin linked list will be picked by the RT scheduler to run. The third and the scheduling class which is used by most of the user space program is the fair class CFS, completely fair scheduler. It has 3 policies: sched normal, sched batch, and sched idle. The idle here is completely different from this idle. Don't confuse between them. This is just for CPU idle, and there is always only one thread which is attached to this particular scheduling class. Sched normal is for all the normal tasks that we use, the shell program to Chrome to anything else. They are mostly on sched normal. Batch is for batch processing, where we want the CPU to run the task for a longer amount of time because of cache hotness or because the data is hot, and it is better to perform them together when the CPU is really idle to do stuff. So we don't take the task away, for example, for 100 to 200 milliseconds of time. And the last one is sched idle. It is for really, really low priority task. Right now the kernel doesn't use it too much, but we are trying to make some use of it in the kernel, but nothing is upstream yet. You want to say something?
What is the default scheduling class for kernel thread? Like, I don't know, system work queue?
I think sched normal only. Yeah. So by default, everything goes through sched normal unless you make it a real-time thing.
Mm-hmm. Okay.
And please feel free to ask questions, because otherwise this whole session will finish in 30 minutes. So if you want to utilize the time, now is the time. Someone? Yeah. And even if you think the question is stupid, it may not be stupid. Please ask.
There was a concept called priority inversion. Like I can change the priorities at runtime. Does any of the policies can do that? I mean to say in the Linux kernel, in the kernel, not user space.
So priority inversion is something else, but we can play with the priorities. When we say priority inversion, I think it is more like, so this is the lowest priority scheduling policy we have, right? So if a task in this policy takes a spin lock, which a task in this policy is trying to take, then that is called as priority inversion, because this is supposed to be the lowest priority task, but it has blocked a high priority task. So this is priority inversion, I believe. And in that case, so the kernel artificially boosts the priority of this thing so that it finishes fast. But what you are asking is a bit different. So we can play with the priorities in the same way we can play with the scheduling policies. So even if we create a K thread or a user thread, it goes through sched normal with a default policy or default priority. But there are APIs available with which you can change the priority of it or the scheduling class and the scheduling policy, anything.
Soft IRQs are done before that, right? Not talking about IRQ, but soft IRQs, you know.
Soft IRQs,
Bottom half.
well, that depends. There are some, so they are run,
Tasklet.
started to be run in the interview context, and
Right.
if they are too long, they are run in a thread.
Is a thread, but
And
priority.
it's a sched normal.
Yeah, it's normal.
Yeah.
Shared normal, but probably with high priority. Maybe the priority is increased because that is mostly used for networking stuff, I think. And right. So the preemption is disabled. So even if there is a high priority round robin or deadline task available, it will not run because we have disabled interrupts. So the scheduler can't do it. So let's go to all the scheduling classes one by one. The highest priority scheduling class available is the stop scheduling class. There is always only one thread which has a policy of stop. The name. So if you try to see it in top or some other debuggers, you may have seen a thread named migration/n. The n here is the CPU number, and migration says that it is a thread which has a scheduling class of stop scheduling class. There can be only one such thread for each CPU, and there is always one thread for such CPUs on SMP system. The stop scheduling class is not available for UP systems because it is used to stop another CPU all the time. So whenever one CPU has to stop other CPU to run some maintenance routine, we use it. But if the system is not SMP, we don't need to stop any other CPU. Because this is the highest priority scheduling class, it can stop anything. But it can't be preempted by anything else because it is the highest priority one. So no other task, so if we queue a deadline task and expect it to run before the currently running stop scheduling class thread, it will not happen. This will not get preempted. This is a kernel mechanism to stop running everything else and run a particular thing. It is mostly used for task migration, CPU hot plug, clock events, RCU, ftrace, and the maintenance of all these things. And deadline is the scheduling class with highest priority where user task runs. This is added recently by Dario and Yuri. It got merged in 3.14 in 2013. There is only one policy in the scheduling class, which is deadline. It is used only for periodic real-time tasks like video encoding, decoding stuff. So one of the characteristics of this scheduling class is if there are multiple tasks already queued for deadline scheduling class and you queue another one, it is possible that your request is rejected because the deadline scheduler, it feels that it cannot accommodate the new request because it doesn't have enough time. We need to guarantee that a task will finish in a finite amount of time for the deadline scheduler. And if it is not possible any further, then the request to put a task into deadline scheduling policy can be rejected.
It was to mention that you don't have to classify the task between each other. For the RT, you have to set this one as a higher priority than another one. In this case, you just describe your task. It's up to the scheduler to decide which task should be scheduled. So you can be preempted by a task, and the next time you can preempt it just to make sure that you will match your deadline.
The next scheduling class is the real-time scheduling class. It is used to run the POSIX real-time task. The priorities are same as what used to be with the O1 scheduler. 0 to 99 are for the RT task, and the other are for the normal tasks. The priorities are inverted here in kernel. So 0 is the highest priority in kernel, while 99 is the highest one in user space. There are two policies we have: FIFO, first in, first out, and round robin. The default time slice for round robin is 100 milliseconds instead of 5 milliseconds, which I was said earlier. Both of them are implemented with simple linked list. So we pick the next task, the top of the linked list, and run it until the time it terminates or it gives the CPU away. These are used for short latency sensitive tasks like IRQ threads. Now this is the scheduling class which is mostly and most widely used in the kernel. Normally everything goes here unless you specify differently. This is, as I said earlier, it was introduced by Ingo into 623 in 2013. It was based on another scheduler which was rotating staircase deadline scheduler by Cornelius. there are three policies: normal, batch, and idle. Normal is for all the tasks. Normal is the policy for by default for everything we do. Batch is for non-iterative tasks which wants the CPU to run the task for a longer amount of time without getting interrupted. And idle is for low, very, very low priority task. So sched idle runs when there is nothing else to run. The implementation of this is quite complicated compared to round robin. It is based on red-black trees. We are not going to get into the details of that, but a red-black tree is a self-balancing tree which balances itself so that you can pick the leftmost node to, and that will be the next task you can run, always. So the red-black tree is organized based on some values. For example, it is vrun time in this case. We'll come to that. And the lowest value will always be on the leftmost node. So you just pick the leftmost node and run it. And as soon as you dequeue the leftmost node, the tree will balance itself again to put the lowest vrun time task on the leftmost node. So what we track here is vrun time, which is virtual runtime. So the basic idea here is that we track the amount of time a task has run, okay? And the task which has run for the least amount of time until now is the task we should pick to run next because it has got the least amount of opportunity until now. Now, if a task has a higher priority, so if there are two tasks, which are, one is higher priority, one is lower priority, we actually want to run the task with a higher priority more. How do we do that? So what we do here is we have something else which is called as the weight of a task. And the vrun time of a task increases based on this weight. So if a task has higher priority, the weight of the task will be more. And because the weight is more, the vrun time will increase slowly. In effect, a task with higher priority will increase its vrun time slowly, and so it will get more chance to run than a low priority task. And the red-black tree is organized based on this vrun time only. So the leftmost node will be the task which has run the least until now and should run now based on its priority. The task priority is calculated as 120 plus nice. So the nice value is, so you can say how nice a task is to all other tasks in the system. So a task with a higher nice value, like plus 19, it is a task which is very, very nice to everyone. So it wants everyone else to run before itself. If a task has a nice value of plus 19, it means that the overall priority will be 139, the lowest in the system. If a task has minus 20 nice value, which means that it is not at all nice, and so it will have a priority of 100, which means that in the user task, it is the task which will run first. Right?
Is the I/O wait taken into consideration for the runtime? I mean, if your application is doing some I/O and waiting for it, will it get a shorter time, or it will?
Doesn't decrease in that case.
No.
Right?
There's no consideration.
So if the application is waiting for I/O, then the vrun time doesn't increase in that case. So yeah.
When the tasks start to sleep or wait for something, we have some way to normalize the vrun time. Just because, for example, if you have two tasks and one task is sleeping for 1 second, for example, so normally its vrun time should not move during this 1 second. If in the meantime a task is waking up periodically, its vrun time will increase. And at the end, when this task that has slept 1 second start to wake up, its vrun time will be really, really low compared to the other one, up to 1 second less, which means that it might run for 1 full second and just stuck the other one. So there is some normalization mechanism to make sure that a task will not steal all the runtime if it wakes up from time to time.
sleeping on, right? I mean, if a task is doing like timer or something that it
No.
wants to wake up in X seconds or milliseconds, and
No.
the other one is doing I/O and is just like waiting for the I/O, but it should be wakened as soon as possible if possible.
No,
There is
you
no
can't have
consideration.
any kind of wake-up latency. And if you have some latency requirement, you should use RT or deadline.
Mm.
So that was CFS. Idle is the scheduling class with the lowest priority. It is not open for any user task. There is only one task ever attached to it, similar to how we saw migration/n here. We have swapper/n here. So whenever you see swapper/012 or something, it is the idle task. So whenever CPU starts to run, so we boot the kernel from the beginning, the kernel sets up so many things. Eventually the same execution context is converted to the idle task of the CPU. Okay, so we create that particular task as the idle task and make the scheduling policy as idle. And this particular idle task is always available to run. Okay, it is always scheduled, always available to run. If there is nothing else left here, then when we start to pick the next task, because there is nothing else here, we pick the task from here, and that is the idle task. The whole thing idle task does is goes to the CPU idle framework, picks how deep we can go into the idle state, as we talked in the previous presentation. We select the deepest idle state possible based on exit latency, entry latency, residency, and all that, and we pick and we go into that idle state, and we go idle. The CPU doesn't run after that unless a wake up happens. So that is the only purpose of the idle class.
How does it relate to CPU frec? Is that totally orthogonal mechanism or?
So CPU frec is used. Oh, where is it? So CPU frec is used only in this part.
Yeah.
After this, the CPU is not there because it is idle.
Yeah, exactly.
So
So,
this is-
it goes. It will
Right.
be on the
So-
slowest there.
Right. So this is CPU idle. This CPU frec uses all this part.
Yeah.
So that is it. Now, how the run queues are defined. So as I told you earlier, the run queue is a queue of tasks which a CPU has to run, right? Now, we have seen there are so many scheduling policies, so many scheduling classes. How does structurally the run queue is defined? So in code, each CPU has a run queue of its own, which is defined by struct run queue. This thing. So an instance of this structure is there for each and every CPU. This bigger run queue, it doesn't have a scheduling policy or scheduling class. It is just a structure to keep all the policies within it. A structure of other scheduling classes which are available to user programs is available here. So this is the CFS scheduling classes instance within the instance of the run queue of the CPU. Then we have RT, then we have deadline. In RT, we will have, inside this, we will have a FIFO and a round robin list. For CFS, we will have a red black tree here, and similarly for DL also, we will have a red black tree inside it. So this is how it is laid out for all the CPUs separately. This is a pictorial representation of the same thing for two CPUs. This is the run queue of CPU 0. This is the run queue of CPU 1. This has one idle task and one stop class task, which are system tasks rather. The size or the height of these three can be different at different point of time for all the CPUs, depending on how many tasks are enqueued for that particular scheduling policy. So in this case, we have more CFS tasks, less real-time tasks, and the same amount of deadline tasks. Here the deadline and real-time tasks are really, really less, and most of what we have is CFS. Yep. So we finished early. 10 minutes more than last one. Any question? Any questions?
So is this it? Or they are not going to invent more scheduler classes? There's not somebody who's like, yeah, I've got this special use case that doesn't fit all of this.
It can happen. For example, deadline was added exactly for this thing. They discussed for a long time that we should add it or not, and then reviews happened, and we finally added. We can do that, but because it is so much core of the kernel, and it is a common piece of code which is used across everybody, so there is too much reluctance to add anything into it. But it can happen. It has happened recently also.
There is something called offline scheduling, right? Isn't there? You take out the CPU and you just run one task on that CPU.
Isolation, I'll say that.
Isolation, yeah.
So isolation is implemented in different ways. So sometimes, so what isolation is that many times, for example, in networking, that's what we used to do in LNG for ODP stuff. What we want to do is we have a user task, we have the whole networking stack in user space instead of kernel, and we want to run the networking stack on a particular CPU. Now we call it isolation because we do not want to do any management work or what do you call housekeeping stuff on that CPU. We don't want any interrupt to land there. We do not want any timers to fire there. We don't want any IRQs, anything else, any other maintenance stuff to happen on that CPU. We just want a particular user task to always run on that CPU, so we use the CPU to the fullest. That is where we use isolation. Now, there are two ways of doing it. One is to isolate the CPU entirely from the kernel, right? So that is isol CPUs. There is a configuration parameter. So with that, the CPU completely goes out of the control of the kernel, and you can do anything on that CPU now. The kernel will not have it. The other way of doing it is that you have the kernel, the CPU is controlled by the kernel and the scheduler, and then you can do it. So one way of doing it is with no hertz idle, full no hertz. So with full no hertz, so on any CPU, all the time we have a tick running, right? Say it is 4 millisecond to 10 millisecond. So every 10 millisecond, a timer will fire on each and every CPU, and that is done for accounting, for keeping a track of time and all that stuff, all the maintenance stuff. So whatever you do, every 10 milliseconds, an interrupt will fire, even if you are running a task. And that is a pain, because that takes the CPU away from the task, and we do maintenance that particular time. But in many cases, this is not really accepted, for example, in the networking stack. So a feature what we have now is full no hertz. So what you can do is using CPU sets. So CPU set is a way of controlling the task that can go to a group of CPUs. So what you can do is move all the tasks away from a CPU, right? And keep only one task on that CPU from user space. You can control this. So when the CPU has only one task to run, the maintenance activity will go away. We will reduce it. So the tick, instead of firing at 10 milliseconds, it will fire at 1 second. We still need the tick because we still have to do some time accounting. The tick is more required for multi-threading, I'll say, because we have to.
I think that now they have been able to remove this.
Oh, I'm not aware of this.
Yeah, they have designed some housekeeping.
With the housekeeping CPUs. So even the 1 second thing is gone now. So now if a CPU is isolated, it can run a particular user thread for all the time with control of the kernel, and we can choose these CPUs and the task to run at runtime from kernel and sysfs. That is all. Sorry?
There is an new API concept where you can trigger the interrupts for a group of packets rather than a single one.
Sorry, can you repeat again? It is on.
Okay. What I'm saying was like instead of triggering the interrupt for every packet, the CPU.
So we are not talking about packets, but we are talking about
just a
devices.
Yeah. Even the Mac is also in a device, right? Here. What I'm saying was there is a concept in the network driver called NAPI. It can handle budget of packets to trigger an interrupt at single moment. That is where they can handle the group of interrupts.
So what you are talking about is the management within the networking stack.
Okay.
What we are talking about here is completely different. So for what we are talking about here is, so you touch the touch screen, you have a device, you touch the touch screen, and the interrupt fires on a particular CPU. Now you don't want to fire that particular interrupt on a particular CPU which is isolated.
Basically, what I'm saying is the similar way, because if one interrupt is coming or one packet is coming in the network MAC, the interrupt will trigger. So ASR of this interrupt driver will getting called. So the NAPI new API is taking care of is creating a budget called group of packets. So once the group of packets is done, it can trigger interrupt instead of triggering interrupts for every packet.
Right. So that is done within the networking stack, and this is within the scheduler.
Okay.
It is taking care of the whole system and CPUs. That is more for the networking thing.
Even in this case, for such situation, that even don't want any interrupt, because interrupt mean that you will have to move from user space to kernel space, which is costly. So most of the time they are even actively pulling the status to react as fast as possible.
And it is getting more and more costly. With Meltdown and Spectre, we have more penalty with the context switch now. Anybody else? Thank you.